disclosures have not changed since yesterday. Okay. So I want to start with an idealized version of a clinical trial. This is the way it was sort of first laid out to me. So you know the treatment effect you're likely to see or hope for. You know what your endpoint, how your endpoint is going to behave, what the variability and standard deviation that endpoint is going to be. You calculate a sample size. I used to look it up in a book. You have two groups of patients. They're going to be the same with respect to all characteristics. You'll randomize them 1-to-1, get blinded treatments. All patients, of course, receive and complete their treatment. They all show up to follow-up. They all provide an endpoint. You analyze the data at the end. There's nothing missing, nothing lagging. And what you get is an unbiased estimate of the treatment effect. And you publish and you're promoted. So that was the way it was originally laid out when I first got interested in this. The problem is that many of these things, of course, are just not true. And two of them I want to address because that's what I'm going to talk about for the next few minutes addresses. One is we're actually incredibly bad at predicting the treatment effect we'll see. It's often back calculated to give you the sample size that you can actually think you can enroll. We're not very good at predicting the variability, and therefore the sample size calculation we do is the exact right sample size for a situation that will probably never occur, and then we have to worry about what happens when we're wrong. And then obviously that we often get outcomes for patients as the trial is being conducted. It's not like all the outcomes come in the last day, and so there's outcomes coming in along the way. Let's talk about how we can use both of those facts and try to design a trial that's more robust and more likely to do the right thing. So we enroll patients over time. The outcomes become available before all the planned patients are enrolled. Typically, that is not always true. We're very bad at predicting treatment effects. We're pretty bad at predicting the variability. So the sample size rarely turns out to be exactly the right sample size. And then a very important point is even if you guessed everything right and the treatment effect was fundamentally exactly what you expected it to be, each trial has its own individual stream of patients coming in that just have their own idiosyncrasies. Sometimes the patients who do well get enrolled early, sometimes they're later. So there's also this variability even if you knew exactly what the true treatment effect was. And so we want a trial design that can do the right thing for the individual data stream that you just happen to get. And every once in a while in the work we do, and we suggest a trial design, people say, well, let's take the data from my last trial and run it through your design. And the thing that I always think is, yeah, but the data you got last time is the one data set I'm sure you'll never see again in your life, right? Because they're all so idiosyncratic. So the general approach is to do something called a group sequential trial. Group means we enroll patients in groups in the sense that we enroll a bunch and then do something, and then enroll a bunch more and do something. The sequential means the groups are enrolled in a sequence, and obviously what we're going to do is interim analyses between these groups in order to make a decision regarding whether the trial should be continued or stopped. So in designing a group sequential trial, the goal is to have an understanding of the risk of drawing a false positive conclusion or a type 1 error where you claim that there really is a treatment effect when there isn't. Now this happens when you get a statistically significant p-value, a p-value less than some criteria we call alpha because we like Greek letters, when in fact the two groups are really not different with respect to their average outcomes. So if there's no underlying difference between the patient groups, the treatment doesn't do anything, on average, the risk of a type 1 error is this cutoff alpha in the simplest situation. But what happens when you take a risk multiple times? So as an emergency physician, my career is based on the fact that people take risks over and over again and it keeps me employed, okay? So the idea is that if you take a risk, that if you keep taking that risk, the overall chance that the adverse event that you're risking occurs accumulates. It compounds, if you will. So when you when you when you make a statistical comparison with a traditional frequentist approach, and the risk of a false positive result, under the assumption that there's no real difference between the groups, is alpha, that if you keep doing more comparisons, there's a higher risk than alpha. And it's the simplest situation where under a number of assumptions, it kind of goes like alpha times the number of comparisons early on. Now, multiple comparisons can be pairwise comparisons. So if you have 3 treatment groups, A, B, and C, you could do A versus B, B versus C, A versus C. That's a type of multiple comparison. You can compare multiple characteristics. I'm going to look at survival time and the incidence of some complicating factor, something else. And those would be multiple comparisons. But the one we're going to focus on is the comparison of 2 groups of patients at multiple time points as you're adding to each of those 2 groups and the trial is enrolling. So in the simplest situation where you have multiple comparisons, you assume the comparisons are uncorrelated, so they have nothing to do with each other. Then roughly the risk of having 1 or more false positive results as the number of comparisons increases goes as alpha times the number of comparisons. This is an approximation. And that's the basis of the Bonferroni correction. The Bonferroni correction says to limit the overall risk of a type 1 error, take the alpha I really want, often 0.05 or 0.025, divide it by the number of comparisons and use that as my new, more stringent criteria for my comparison. That's the Bonferroni correction. How someone got their name tied to divide by the number of tests, I have no idea. Very good marketing. Okay? So in order to correct this, we just divide by the number of tests. We have a more stringent criteria, and that brings the experiment-wise or the trial-wise risk of a type 1 error back down to the number we wanted, typically 0.025 one-tailed. Okay. I'm ahead of myself. That's what we're going to do. Okay. So let's talk about interim analyses from an ethical point of view. So let's suppose you have an illness, I'm sorry, and you present to your own hospital, I'm now doubly sorry, and a resident who has a resident research requirement, third thing to be sorry about, runs up to you and they are so happy. Dr. Lewis, I'm so happy to see you because I've enrolled 99 patients in my trial. I need 100 patients. You're the 100th patient with this disease. Will you please let yourself be randomized? Well, I'm thinking to myself, maybe we didn't know what the right treatment was when they started this trial, but now that we have 99 out of 100 patients worth of information, the information exists so that I don't want to be randomized. I just want to look at the data and choose my therapy, right? So it's sort of a counterintuitive thing for most people that we pretend in most trials at the very end that we were just as ignorant as we were at the very beginning. So from an ethical point of view, it's important that we stop new randomization in trials as soon as we can draw a reliable conclusion regarding the comparative effectiveness of the arms being tested, so that we don't randomize people where one, we probably know what we should actually give them, and number 2, when we're disingenuous in saying that we need to randomize them in order to still learn. So, interim analyses are a type of multiple comparison. We do want to control the type 1 error risk so we don't publish trials that have false positive results. So we have to have a pre-planned or pre-specified way of spreading our risk of a false positive conclusion over the possible times at which we might stop the trial and claim that there is a difference. But if the outcome data accrue quickly enough, and what I mean by that is if after you enroll the patient, their outcome is known soon enough so you can learn from it while you're still enrolling, then we really should be using interim analyses when we are studying diseases that have significant morbidity or mortality. This is much less important if the disease is something that's, self-limited and people don't worry too much about it. But if we're studying serious illness or injury, we shouldn't keep randomizing people beyond when we should probably know the answer. So the way we do this is we set up these sub-alphas. They're the little alpha 1, 2, 3, 4 at the bottom. And those are the criteria against which we would compare a p-value calculated at each point in the trial in order to claim that the trial had demonstrated a difference between the groups. So to control the overall type 1 error risk, we make these alphas smaller than 0.025 one-tailed so that we control the overall risk of a type 1 error across this entire planned trial. If we didn't have the interim analyses, alpha sub 4 would be 0.025. By the way, the reason I'm always using 0.025 instead of 0.05 is a personal vendetta I have against two-tailed testing, okay? I don't know any of you who are testing therapies and you're equally interested in harming people as helping them, okay, which is what's implied by a two-tailed test. So I always try to think in terms of a one-tailed way. So these alphas have to be more stringent. And so how do we figure out how stringent they should be? Well, we call these things nominal alpha levels because there's these criteria against which we're going to compare the p-values. And we can spread this risk of an error in different ways across the different interim analyses. We can be really conservative early on and make it really hard to stop the trial early and spread a little more risk of a false positive later. Or we can spread it relatively evenly across the interim analyses. So the simplest way to do this conceptually is called a Pocock design, and you just find a number, I'll get to that in a second, which is a criteria which you compare the p-value, and you make the number the same at all the interims in the final analysis. That's called the Pocock design. It's developed by a gentleman named Stuart Pocock. I once had the privilege of standing on a stage with him discussing interim analysis, and the first thing he said is, I, Stuart Pocock, would never use the Pocock design, okay? I then had to present slides like this that mentioned the Pocock design, which was entertaining at the time. So the reason Stuart Pocock and really the rest of us would virtually never use a Pocock design is the general feeling is that early on in a trial, there's a number of things that make the population potentially a little less representative of the whole population. You may not have your data collection quite right. There's a general distrust of small numbers, which may or may not be rational depending on the setting. And so most people think you should be more conservative early on, meaning very small numbers against which you compare your p-value, and you can be less conservative later on in the trial. So the most common way of doing this is what's called an O'Brien-Fleming design, which is just a way of spreading out the risk of the type 1 error that goes from very conservative to less conservative. That approach also generally is going to result in a smaller required total sample size. So it's very common. So unless you have a compelling reason not to do this, you should use the O'Brien-Fleming approach to group sequential design. Okay. Now, this is a little bit of a subtle point, but it's important, which is to realize that if I'm in the second or third interim analysis and I'm comparing the data in my two groups, some of those patients that I'm including in that analysis, I already included in a prior analysis, right? I calculated a p-value after the first group. All those patients are included in the data when I calculate the second or the third interim analysis p-value. Is that clear? That creates a correlation between the p-values. So if the first one looked almost significant, though that difference that led to that is included into the subsequent data. Because of that, those little alpha cutoffs, should have changed this slide, when you add them up, can be greater than your overall type 1 error risk, and that is okay. So it's very counterintuitive. In Bonferroni, we just made it so that the if you added up the alpha cutoffs for the multiple comparisons, they exactly equal 0.05 or 0.025 because we just divided by the number of tests. Here it adds up to more than the total, than your planned total risk of the type 1 error, and it works out, but it works out because you're using the same patients in multiples of the tests. Okay, so having shown that, here's some example of what the cutoffs actually look at. So let's take the one where I put the brackets. So in that design, you have two interim analyses. They would typically occur at 1/3 and 2/3 of the patient enrollment, or 1/3 and 2/3 of the endpoints being available for analysis. The first time you would compare the p-value you get against 0005. If you're not statistically significant, you would continue. In the second one, you would compare your p-value against a 0.0141. Again, I'm using the O'Brien-Fleming design. And if you have to go to the end, because you don't stop for efficacy early, you can compare the p-value against 0.0451. This is awfully close to 0.05, so you haven't lost much power with the same sample size compared to not doing the interim analyses. So the interim analyses give you an opportunity to stop early if there's a larger than expected treatment effect, or maybe just a good treatment effect. And you don't lose too much power because you don't have to be that much more stringent at the end if you spread the alpha risk this way. So the upside is possibility of stopping early. The downside is a little loss of power, or conversely, needing a few extra patients to achieve the same power as you would have had with a simpler design. If you had used the Pocock design, you would have been much more conservative at the end. You're going to need a significantly bigger trial in order to get the same power. Now, that approach requires knowing when you're going to do the interim analyses. And if there's one thing that you've probably figured out from at least your small group discussions, is it's really hard to plan clinical trials. It's really hard to know when things are going to happen. It's hard to make an interim analysis occur at an exact time point. So you can implement a very similar approach using something called an alpha spending function. And the reason I'm going through this is not because I expect you to write out an alpha spending function, it's so that you know what this phrase should look like in your grant, frankly. The alpha spending function allows you to be flexible in the timing of your interim analyses. And what it does is it pre-specifies the speed at which you're spending your type 1 error risk as the trial progresses. And I'll try to make this more concrete in a second. So the idea is that I'm going to spend my alpha as time goes on, and the function is the red line. It starts as 0 because before I start, I've not considered stopping. If you don't stop for success, you can't have a type 1 error. And at the end, I want to expend all my risk of a type 1 error, because the more risk of a type 1 error I can spend, the more chances I have to actually detect a real treatment effect. Okay? The shape of the function determines this balance between how much risk you spend early versus late. This shape tends to spend less early, like O'Brien-Fleming, and more late. Okay? Basically, the time at which you end up deciding you can do an interim analysis, you get your queries resolved, your data set's available, your statistician has some time to do it, determines what the alpha is at that interim analysis. Unfortunately, for simplicity, that alpha right there is not the alpha cutoff in general. This is the actual amount of risk you're spending, but because of that little correlation detail, it's a little different than what the cutoff is. You don't have to worry about this, the software will work it out. But these alphas you never see, they add up exactly to 0.025 or 0.05. Okay, but they correspond to alpha cutoffs that then you compare your p-value to. And this is all built into a large number of different software packages. So the advantage of the alpha spending function is it allows you flexibility in when you actually do your interim analyses. It is a completely pre-specified design, so it has good statistical characteristics. So what I typically see in the methods section of a grant is that we're going to do a clinical trial with a maximum sample size of blah. There will be this number of interim analyses. We'll be doing 2 interim analyses approximately at 1/3 and 2/3 patient enrollment, but we will use an O'Brien-Fleming boundary with an alpha spending function. Period. That tells me everything I need to know about your interim analysis plan for efficacy and early stopping for efficacy. Okay? How do you figure out the power and sample size of this sort of thing? Well, you can do all kinds of math, or you can download a free software package, which, according to the thing that says you can't see in the upper left, I downloaded the free version for 30 days. I have no financial association with this company, but this is a very commonly used package. It's NCSS Pass. This is an old version. But you basically put in what you're doing. I have no idea why I use an example with an alpha of 0.15. We'll ignore that. The treatment effect I'm looking for is 0.5 to 0.6. The number of interim analyses I'm doing, a few details, and it says spending function calculation. That tells me I'm using an alpha spending function, and it says O'Brien-Fleming analog, which means this is the alpha spending approach to an O'Brien-Fleming. And then I hit a button. And what it tells me is exactly how many patients I need for various power. And it just gives me everything I need. Okay, so if you don't want to buy the software, you can download it, do your analysis, put it in your grant. Yeah.
Just so you know, the reason your alpha is 0.15 is because it's the free trial.
Yeah.
So.
Oh, I have to pay to get a good answer?
Yeah.
Okay, so if you don't want to spend money, you can go to this slide and use the equivalent R function, which is free, right? Okay. Okay.
You knew that.
I knew the R was free. What I didn't know is that my cheapness resulted in me having to have a dumb example on a slide. Okay. If you use these, this is the kind of thing you get. So I just happened to do this as a pocock. I did this to sort of exaggerate the difference in sample size. So first, for this trial, we're trying to define and detect an increase in a dichotomous endpoint survival from 40% to 60% with treatment. We're going to do a two-tailed 0.05 or a one-tailed 0.025. And if you do just a simple sample size correction, which you can do with either of these software packages, that requires a fixed sample size of 107 patients with outcomes in each group. So the fixed sample size with no opportunity for early stopping, you require 214 patients. If you used a pocock design, which is going to have more inflation of the required sample size, and remember, 2 interims and a final is 3 groups. Each group has to have 78 patients, so the total sample size is increased to 234. So that's the increase in sample size with this design, and remember this is an exaggerated case, to get me the same power but also allow me the opportunity for early stopping, okay? But the thing about a group sequential design is that it is adaptive in the sense that the actual number of patients you need depends on the difference that actually accrues within your patient population. So, for example, let's suppose you're in the null case where in both treatment groups, half the patients on average die, and there's no difference. Then, because you had no early stopping for futility, which we'll get to in a second, the trial tends to go to the end, the full 234. The average required sample size is 230, and frankly, whenever it stops early, it's for success. That's actually a type 1 error. And the type 1 error rate, when I simulated it, was about 0.044. Okay? But let's suppose the treatment works, and it works exactly as well as we hypothesized when we powered the trial, so 0.4 and 0.6 for the 2 survival rates. Then on average, the sample size is 165. Now the sample size is never actually 165. It's either 78 or what should I say, 158? I hope I have that, 156, okay? Or the full 234. Those are only the 3 options because it's a group sequential trial. But in general, on average, it stops around the second interim analysis, and you get the power that you designed of about 80%. But what happens if the treatment works really well? Remember I said we're very bad at predicting treatment effects? Let's say we underestimated how well it works. So now I'm going to digress. So the DAWN trial was mentioned yesterday. The DAWN trial was a trial that some of us participated in designing. It was endovascular therapy for LVO stroke. And I remember clear as day a discussion I was having where we were trying to decide where the interim analyses should be and how big the trial should be. And the investigators felt very strongly that when they pulled a clot out, they achieved miraculous outcomes. And as a statistician and also a somewhat jaded emergency physician who saw neurologic diseases as largely untreatable, I thought they were absolutely crazy. So we had this argument about how big the trial needed to be. It had a maximum sample size of 500, and we put the first interim analysis way down at 200. And I thought to myself, you guys are crazy to spend any alpha at 200 because that's never going to happen. As you may well know, at 200 the sample size was, the treatment effect was much larger than any of us could have imagined, and it stopped immediately at 200 with the publication of the results. So we can be wrong in both directions. Here, if the treatment effect is bigger than we expect, it almost always stops at the interim near 78, on average of sample size of 86 with essentially perfect power. So the point is that it adapts its sample size to what the treatment effect turns out to be, rather than forcing you to pick a sample size assuming you and hope you got the treatment effect right. That helps match the resources required to the trial to the resources required to show a treatment benefit, and helps you say to a patient, we're still enrolling, and that means we don't yet know the answer, so it's still ethically appropriate to enroll. So that ties us back to that ethical consideration early on. Now, at the low efficacy side of that consideration, we're still enrolling almost all the patients. And as we do interim analyses, sometimes what we learn is there's really no hint of a difference early on. And we really should think about stopping for futility, because it is also not appropriate to continue to enroll patients when in fact there's no longer a meaningful chance that the trial will show a difference, right? We tell people we're involving them in research because we hope to show benefit. If that hope fades, we need to do something about that. So we can add a futility stopping rule. So for example, we can say if the p-value is too big, and by the way, these are different cutoffs, that we are going to stop for futility. Now, last year when I gave this talk, someone asked a question about something called a beta spending function. So the alpha spending function was spending the type 1 error risk over time, the false positive risk. A beta spending function spends the risk of a false negative, stopping and declaring futility or no difference. But it's simply another way of mathematically dealing with futility. So I just want to say those last two bullets are functionally the same in this setting. So here's what the behavior looks like. As you go from a situation where there's no treatment effect, the null hypothesis, out to the one where there's the treatment effect you had originally hoped for, the power of the trial increases. And as a general rule, we should try to power our trials for 90 or 95% because we want a negative result to be just as meaningful or close to as meaningful as a positive result. If we do that and we use a group sequential approach, then on average, as the actual treatment effect gets bigger, the true treatment effect, the average sample size required will fall, so we enroll running trials longer than we have to in order to demonstrate that benefit. But on the left side, we have this problem that we're continuing trials when we really should stop because this isn't really going to show anything. If we add a futility rule, we can lower it on that side as well, and most of the trials that are being run on treatments that actually don't have a clinically important true treatment difference will stop early once it's no longer realistic to believe that trial might continue on and show a benefit. So as a general rule, I talked about what I would look for in the description of the design for efficacy. The next paragraph would say, in addition, we're going to use a futility rule. There's a number of different ways to do that, and I would point you to an article, a 2-page article in JAMA on futility in clinical trials that sort of lays out this. If anybody emails me, I'll send you the PDF. So that if at the interim analyses the chance of the trial ultimately showing a difference is too low, we will terminate the trial. Okay? So I do want to make one comment about sort of the bizarre incentives in research. So if for example, Kurt and I are consulting for a company that has multiple products in development, and every dollar they save in one program, they can invest in some other program. That company will typically be very interested in stopping a trial as soon as it no longer has benefit. So they're going to want to stop for futility. They're obviously going to want to stop for early success. That has business implications. If I'm doing consulting, I'm trying to be politically correct here, for a company that has a single product for which the failed trial means everybody loses their job because the venture capital goes away, their affection for early stopping for failure might be different. Okay? If I'm doing NIH-funded research and I stop early for futility, and all of the support from my administrative staff, my lab, and everything goes away, I may also have different incentives. So I just want to point out that we should really be basing our choice of design based on the fact that we are experimenting on human beings and what the right thing to do is in experimenting about human beings. As you talk to people about designs, you should just be aware that sometimes other incentives come into play, and you should think very carefully about how you can address those so that we all do the right thing. All right. One of the concerns about early stopping of clinical trials has to do with the fact that there is a resulting bias in the estimate of the treatment effect. So the idea is that we're testing to see if we met some statistical criteria, and there's some random noise. And therefore, if the treatment effect is this big, but there was some random noise that made it look this big, we're more likely to stop than if the random noise was in the other direction. Okay, that creates bias so that a clinical trial that stops early for success will produce an estimate that is very slightly biased in the positive. This has received a lot of discussion in the statistical and some of the clinical trials literature. It is a concern that in all reasonably designed trials has absolutely no clinical significance. It's not a degree of bias that makes a treatment you would want to adopt, that you would not want to adopt look good, okay? And Kurt has done work showing about the quantification of the bias. I'm bringing this up so that if you hear the comment, you can't trust the results of the trial that stops early, you should ask yourself, did it stop early at a planned interim analysis? And if the answer is yes, then you really can trust it to the degree that you can trust, clinical research in general. Okay. So if you're studying a disease that has significant morbidity or mortality, and the outcome is available soon enough for you to act on it during the conduct of the trial, you should virtually always incorporate planned interim analyses into your design. In doing so, you have to pre-specify a plan for spending your risk of a false positive result. The most appropriate and easily defendable approach is the O'Brien-Fleming. There's no reason to give up the flexibility of choosing the timing of your interims, so you should use an alpha spending approach. If the treatment has any morbidity associated with it, you also want to make sure you have a futility stopping rule. Futility stopping rules cut down your power a little bit, so they need to be calibrated for your situation. But I think they are ethically imperative so that when we tell people we're randomizing them with the hope of learning something, that hope is actually still real. I'll stop there. I'd like to point out I'm now 1 minute early, and happy to take any questions. Any questions?